Hello friends, in today's lecture we shall first conclude that the discussion we had on electric and magnetic fields in last few lectures can be summarized in only 4 equations known as Maxwell equations. Second, we examine the science and engineering of magnetic materials. The careers of many scientists and engineers are focused on understanding why some materials are magnetic and others are not, and how existing magnetic materials can be improved. These researchers wonder why Earth has a magnetic field, but you do not. They find countless applications for inexpensive magnetic materials in cars, kitchens, offices, and hospitals. And magnetic materials often show up in unexpected ways. For example, if you have a tattoo and undergo an MRI scan, the large magnetic field used in the scan may noticeably pull on your tattooed skin because some tattoo ink contains magnetic particles. In another example, some breakfast cereals are advertised as being iron fortified because they contain small bits of iron for you to ingest. Because these iron bits are magnetic, you can collect them by passing a magnet over a slurry of water and cereal. Our first step here is to revisit Gauss law, but this time for magnetic fields. Figure shows iron powder that has been sprinkled onto a transparent sheet placed above a bar magnet. The powder grains, trying to align themselves with the magnet's magnetic field, have fallen into a pattern that reveals the field. One end of the magnet is a source of the field. The field line diverges from it, and the other end is like a sink of the field. The field lines converge toward it. By convention, we call the source the north pole of the magnet and the sink the south pole, and we say that the magnet with its two poles is an example of a magnetic dipole. Suppose we break a bar magnet into pieces the way we can break a piece of chalk. We should, it seems, be able to isolate a single magnetic pole called a magnetic monopole. However, we cannot, not even if we break the magnet down to its individual atoms and then to its electrons and nuclei. Each fragment has a north pole and a south pole. Thus, the simplest magnetic structure that can exist is a magnetic dipole. Gauss law for magnetic fields is a formal way of saying that magnetic monopoles do not exist. The law asserts that the net magnetic flux through any closed Gaussian surface is zero, that is, phi b is equal to cyclic integral of b dot dA, which is equal to 0. Contrast this with Gauss law for electric fields. Phi b is equal to cyclic integral of E dot dA, which is equal to Q encircled upon epsilon 0. In both equations, the integral is taken over a closed Gaussian surface. Gauss law for electric field says that this integral, the net electric flux through the surface, is proportional to the net electric charge enclosed by the surface. Gauss law for magnetic fields says that there can be no net magnetic flux through the surface because there can be no net magnetic charge enclosed by the surface. The simplest magnetic structure that can exist and thus be enclosed by a Gaussian surface is a dipole, which consists of both a source and a sink for the field lines. Thus, there must always be as much magnetic flux into the surface as out of it, and the net magnetic flux must also be zero. Gauss' law for magnetic fields holds for structures more complicated than a magnetic dipole, and it holds even if the Gaussian surface does not enclose the entire structure. Gaussian surface 2 near the bar magnet encloses no poles, and we can easily conclude that the net magnetic flux through it is zero. Gaussian surface 1 is more difficult. It may seem to enclose only the north pole of the magnet because it encloses the label N and not the label S. However, the south pole must be associated with the lower boundary of the surface because magnetic field lines enter the surface there. The enclosed section is like one piece of the broken bar magnet. Thus, Gaussian surface 1 encloses a magnetic dipole and the net flux through the surface is zero. Induced magnetic fields. In earlier discussions on magnetostatics, we saw that a changing magnetic flux induces an electric field, and we ended up with Faraday's law of induction in the form cyclic integral of E dot ds is equal to minus d phi b upon dt. Here, vector E is the electric field induced along a closed loop by changing magnetic flux encircled by that loop. Because symmetry is often so powerful in physics, we should be tempted to ask whether induction can occur in the opposite sense. That is, can a changing electric flux induce a magnetic field? The answer is that it can. Furthermore, the equation governing the induction of a magnetic field, that is cyclic integral of B dot ds, is equal to mu 0 epsilon 0 into d phi e upon dt, is almost symmetric with the equation of Faraday's law of induction, that is equation A. We often call it Maxwell's law of induction after James Clerk Maxwell. Here, vector B is the magnetic field induced along a closed loop by the changing electric flux in the region encircled by that loop. Charging a capacitor. As an example for this sort of induction, we consider the charging of a parallel plate capacitor with circular plates. Although we shall focus on this arrangement, a changing electric flux will always induce a magnetic field whenever it occurs. We assume that the charge on our capacitor is being increased at a steady rate by a constant current I in the connecting wires. Then the electric field magnitude between the plates must also be increasing at a steady rate. Figure B is a view of the right hand plate of figure A from between the plates. The electric field is directed into the page. Let us consider a circular loop through point 1 in figures A and B, a loop that is concentric with the capacitor plates and has a radius smaller than that of the plates. Because the electric field through the loop is changing, the electric flux through the loop must also be changing. According to Maxwell's law of induction, that is equation B, the changing electric flux induces a magnetic field around the loop. Experiment proves that a magnetic field is indeed induced around such a loop, directed as shown. This magnetic field has the same magnitude at every point around the loop and thus has circular symmetry about the central axis of the capacitor plates. If we now consider a larger loop, say through point 2 outside the plates in figure A and B, we find that a magnetic field is induced around that loop as well. Thus, while the electric field is changing, magnetic fields are induced between the plates, both inside and outside the gap. When the electric field stops changing, these induced magnetic fields disappear. Although Maxwell's law of induction is similar to Faraday's law of induction, the equations differ in two ways. First, equation B has two extra symbols, mu0 and epsilon 0, but they appear only because we employ SI units. Second, equation B lacks the minus sign of equation A, meaning that the induced electric field and the induced magnetic field have opposite directions when they are produced in otherwise similar situations. Ampere-Maxwell law. Consider here the left side of Maxwell's law of induction, that is equation B. The integral of the dot product around a closed loop appears in another equation, namely Ampere's law. Cyclic integral of B dot ds is equal to mu0 into I encircled. Here I encircled is the current encircled by the closed loop. Thus, our two equations that specify the magnetic field produced by means other than a magnetic material, that is by a current and by a changing electric field, give the field in exactly the same form. We can combine the two equations into the single equation. Cyclic integral of B dot ds is equal to mu0 epsilon 0 into d phi E upon dt plus mu0 into I encircled. When there is a current but no charge in the electric flux, such as with a wire carrying a constant current, the first term on the right side of equation C is 0, and so equation C reduces to Ampere's law equation. When there is change in electric flux but no current, such as inside or outside the gap of charging capacitor, the second term on the right side of equation C is 0, and so equation C reduces to equation B, that is Maxwell law of induction. Learning objectives of displacement current. After going through this section, you should be able to identify that in the Ampere-Maxwell law, the contribution to the induced magnetic field by the changing electric flux can be attributed to a fictitious current known as displacement current. To simplify the expression, identify that in a capacitor that is being charged or discharged, a displacement current is said to be spread uniformly over the plate area from one plate to the other. Apply the relationship between the rate of change of an electric flux and the associated displacement current. For a charging or discharging capacitor, relate the amount of displacement current to the amount of actual current and identify that the displacement current exists only when the electric field within the capacitor is changing, and apply the Ampere-Maxwell law to calculate the magnetic field of a real current and a displacement current. Displacement current. If you compare the two terms on the right side of Ampere-Maxwell law, that is equation C, you will see that the product epsilon 0 into d phi E upon dt must have the dimension of a current. In fact, the product that has been treated as being a fictitious current called the displacement current I is equal to epsilon 0 into d phi E upon dt. So we can write equation C as cyclic integral of B dot ds is equal to mu 0 into id encircled plus mu 0 into I encircled. Here id encircled is the displacement current that is encircled by the integration loop. Let us again focus on a charging capacitor with circular plates as in part A of figure. The real current I, that is charging the plate, changes the electric field between the plates. The fictitious displacement current ID between the plates is associated with that changing field. Let us relate these two currents. The charge q on the plates at any time is related to the magnitude E of the field between the plates at that time, and the plate area A by q is equal to epsilon 0 into A into E. To get the real current I, we differentiate with respect to time, finding dq upon dt is equal to I, which is equal to epsilon 0 A into dE upon dt. To get the displacement current ID, we can use displacement current equation D, assuming that the electric field between the two plates is uniform. We neglect any fringing. We can replace the electric flux in this equation with EA. Then equation D becomes ID is equal to epsilon 0 into d EA upon dt, which is equal to epsilon 0 into A dE upon dt. Looking at the equations F and G, we see that the real current I charging the capacitor and the fictitious displacement current ID between the plates have the same value, that is ID is equal to I. Thus, we can consider the fictitious displacement current ID to be simply a continuation of the real current I from one plate across the capacitor gap to the other plate. Because the electric field is uniformly spread over the plates, the same is true of this fictitious displacement current ID as suggested by the spread of current arrows in figure B. Although no charge actually moves across the gap between the plates, the idea of the fictitious current ID can help us to quickly find the direction and magnitude of an induced magnetic field. Finding the induced magnetic field. Earlier, as we found the direction of the magnetic field produced by a real current I by using the right hand rule, we can apply the same rule to find the direction of an induced magnetic field produced by a fictitious displacement current, as is shown in the center of this figure for a capacitor. We can also use ID to find the magnitude of the magnetic field induced by a charging capacitor with parallel circular plates of radius r. We simply consider the space between the plates to be an imaginary circular wire of radius r carrying the imaginary current ID. Then the magnitude of the magnetic field at a point inside the capacitor at radius r from the center is given by this equation. B is equal to mu 0 ID upon 2 pi capital R square into R. Similarly, the magnitude of the magnetic field at a point outside the capacitor at radius r is B is equal to mu 0 into ID divided by 2 pi r. Maxwell's equations. This table here sums up the four fundamental equations of electromagnetism called Maxwell's equations. These four equations explain a diverse range of phenomena, from why a compass needle points north to why a car starts when you turn the ignition key. They are the basis for the functioning of such electromagnetic devices as electric motors, television transmitters and receivers, telephones, scanners, radar, and microwave ovens. The first equation relates net electric flux to net enclosed electric charge. The second relates net magnetic flux to net enclosed magnetic charge. The third relates induced electric field to changing magnetic flux, and the fourth relates induced magnetic field to changing electric flux and to current. Maxwell equations are the basis from which many of the equations of electrostatics can be derived. So friends, here we come to the end of our discussion in this lecture, and therefore we sum up. The simplest magnetic structures are magnetic dipoles. Magnetic monopoles do not exist. Gauss law for magnetic fields states that the net magnetic flux through any Gaussian surface is zero. It implies that magnetic monopoles do not exist. A changing electric flux induces a magnetic field. Maxwell's law relates the magnetic field induced along a closed loop to the changing electric flux through the loop. Ampere's law gives the magnetic field generated by a current encircled by a closed loop. The idea of a displacement current allows us to retain the notion of continuity of current through a capacitor. However, displacement current is not a transfer of charge. Maxwell's equations summarize electromagnetism and form its foundation, including optics. So that is it for today. See you in the next lecture, where we shall discuss more about magnetostatics. Thank you very much.